Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Amirah Husna binti Muhammad Hazlan. My metric number is 304078. Today I'm showing how to partially differentiate the quantity equation Q with respect to the price of substitute PS. The equation is given as a function that includes PS inside a bracket. Since we are only focusing on PS, we ignore all other variables and constants. We spot the term CPS and differentiate that. The derivative of CPS is just C, and since it being multiplied by F, we get FC. Then we divide that by the constant F plus B because it's in the denominator. Now, let's look at the relationship between quantity Q and the price of substitute PS. After partially differentiating Q and with respect to PS, we found that the result is a positive value. Since all the constant F, C, and B are positive, this derivative is also positive. A positive derivative means that as the price of the substitute increase, the quantity demanded of the good Q also increase. This shows a positive relationship between the two variables. In simple terms, when the substitute becomes more expensive, consumers tend to switch to this product instead, so its demand goes up. Now, let's briefly explain the effect of change in PS, which is the price of substitute on the quantity Q. From the previous part, we saw that the relationship between Q and PS is positive. This means that when PS increase, for example, if the substitute becomes more expensive, consumers are likely to shift their demand to other products instead. As a result, the quantity demanded for other good Q will increase. On the other hand, if the price of substitute decrease, then more people will switch to the substitute and the demand for other good Q will fall. In short, the effect is straightforward. An increase in the price of substitute leads to an increase in Q, and a decrease in price of substitute leads to a decrease in Q.
Hello and Assalamualaikum. My name is Nur Nabila Kristina binti Muhammad Adili. My matrix number is 304163. So in this short presentation, I'll explain how an increase in the price of input denoted by R affects the market equilibrium of a particular good. So we will use a simple supply and demand model to and apply total differentiation to support our explanation. Next, to analyze how R affects equilibrium, we rewrite the system as F1 equal to Q minus dPy is equal to 0 as a demand equation, and F2 is equal to Q minus SPR equal to 0 as a supply function. Next, we apply total differentiation to both equations. For F1, dQ minus d1 dP minus dy dy equal to 0, and for F2, dQ minus sy dP minus sr dr equal to 0. So this form a system of two equations with two unknowns, dq dr and dp dr. We represent the system in matrix form as follow, and we compute the determinant of the coefficient matrix, and we got negative SP plus dP. So since SP is more than 0 and dP is less than 0, the determinant is negative, meaning the matrix is invertible and the system has a unique solution. Next, for the economic interpretation, because SR less than 0, when the input price R increases, the supply curve shifts to the left, and this results in a higher equilibrium price and a lower equilibrium quantity. So to conclude, when the input price increases, it raises production costs, and this causes the supply to decrease, leading to a higher price and lower quantity in a market equilibrium. Thank you for listening, and I hope this explanation was clear and helpful.
Today I will explain a set of questions based on the co-plus production functions, which is Q equal to K power of 0.4 and power of 0.6. where Q is output, K is the amount of capital, and L is the amount of labor. Let's go through each part of the questions together. Now for the questions A, we need to find the marginal product of capitals, which is the marginal product of capital, or APK, shows how much additional output is produced when one more units of capital is used, keeping labor constants. To find APK, we take the partial derivative of Q with respect to K, which is formula is APK equal to partial derivative Q, partial derivative K. So we get the answer 0.4 K to the power of negative 0.6 and power of 0.6. This means that every additional units of capital, output is increased, but a rate that depends on current levels of both capital and labor. Now we move out to the second question, which is B. We need to find marginal product of labor. Next to marginal product of labor, or MPL, shows the change in output from using one more units of labor holding capital constants. We take the partial derivative Q with respect to L. So the formula is MPL equal to partial derivative Q, partial derivative L. You will get the answer 0.6 K power of 0.4 and the power of negative 0.4. So this tells us that output increased with more labor, but at a decreasing rate due to the negative exponent on L's. Now we move on to another question, which is C. We need to find the average product of capitals. Now let's look at the average product of capital, or APKs. This shows the output decrease. This shows the output produced by unit of capitals. The formula is APK equal to Q over K. So we will get the answer Q power of 0.4 and the power of 0.6 over K. So the answer is K the power of negative 0.6, the power of 0.6. This means that as capital increase, the average output per unit of capital decrease, showing the ratio against the capital. However, if labor increase, APK goes up.
Next, I will explain about the average product of labor. The average product of labor, or OPL, is APL equal to Q divided by L equal to K power of 0.4, L power of 0.6 divided by L equal to K power of 0.4 divided by L power of 0.4. This shows how much output is produced on average by each unit of labor. Now, let's interpret the numbers 0.4 and 0.6. In the production function, the value of 0.4 is the output elasticity of capital. This means if we increase capital by 1%, output will increase by 0.4%, assuming labor stays constant. The value 0.6 is the output of elasticity of labor. So, the 1% increase in labor will raise output by 0.6%, holding capital is constant. When we add both elasticities, 0.4 plus 0.6, we get 1. This tells us the production function has constant returns to scale, meaning if both inputs double, output will also double. So, that's all for question number 3.